Hello everyone. In this section, we're going to do oscillation of a mechanical system. Okay, so this section may be a little bit difficult, but this is the application of the whole chapter 8, and it's pretty interesting, especially for the mechanical engineer student. You may have already seen this kind of problem in other class, or maybe in the future you will see this kind of problem. Okay, firstly, let's take a look at the statement of the problem. So this is a real life problem. We're going to set up a model and then use what we learned in 8.1 till 8.3 to solve this kind of problem. Statement of problem, let's see. A mass of m kg is attached to the end of spring. So we have a spring, okay, and whose natural length is L0 or L0. So we have a, let's see. Firstly, we have a spring. I'm going to draw the graph, okay, and looks like this. And the natural length is, so natural length is L0. Okay. And let's when t equals 0, the mass is displaced y0 meters from its equilibrium position. So when we attach something to the end of the spring will go down a little bit and stay there, right? It's stable. And the natural length is L0, so I'm going to write down the length from here to here actually is L0, the natural length. And equilibrium position, we say the equilibrium position y equals 0. And next, when we pull the mass is displaced, okay, when we pull this down a little bit like a y0 and then release it with a velocity v0. Actually, they are just initial conditions. We are going to use them later. Firstly, we want to set up the differential equation. And then when we release the mass, the object, definitely it will go up and down and move. Because it's spring, right? It will oscillate, move up and down. And we want to see what is the position for the object after time t. So we say this is yt. We say the yt, and okay, maybe here it doesn't matter too much. So we say here is the position yt. What is the position after time t? Firstly, let's take a look at spring. Spring, we have there is a Hooker's law for the spring. Spring, for the object, it has the force made by spring, okay, given by spring. So we say Fs. And for the object, because the spring pull the object up, so definitely this is F goes up. And for the object, it also has the gravity. We say that is mg, given by Fg. And for the spring mass, which is Fs equals negative k times the length of the spring. So for the length of the spring, we add L0 plus yt. So you can see here we have the spring force and the gravity force. Okay, so we say here's the first force. The second is gravity, which is given by Fg. We say this is mg. Sometimes, okay, if we add some damping force, I don't know if you have already heard about this or not. Damping force means kind of resistance. So if we add like a damping force, so here we have some like a fluid, and this gives some resistance. Okay, this is damping force. For example, if we can look at the door, when we shut down the close the door, there is damping force actually inside the door, because the door can close slowly because there's damping force inside. Okay, if we add damping force to it, so what's the damping force? we say FD. Damping force is like a proportional to the velocity. So we say the velocity, which is position derivative, which is dy dt, proportional to velocity. Okay. And it's negative because it's a resistance. Okay, resistance, like a similar to friction. And the C is called damping constant. C is called damping constant, and it's positive. This C is similar to the K. K is the spring constant. So for each spring, we have a constant. Okay. So this. And if we add any like external driving force, and for the external we say Ft. So this is just a general model, but for our class, we will do some simple model, so we don't have extra force. Don't worry too much, but I just want to give you the general case. So what is Newton's second law? That means ma equals F, right? So ma equals F, Newton's second law. So A is second derivative of the position. That's the acceleration. We learned this in calculus 1. Ma, which is the total force, so we add Fg, Fs, F damping force, and also the external force. So we get this thing. Now we plug in all the forces. So m d squared y dt squared, which is Fg is mg, and Fs, which is negative, the force given by the spring, K L naught plus y t. Oh, we just write down y here. Okay, y means the function we are going to solve. And damping force, C dy dt plus Ft. And next, we want to write down this a little bit better. We want to write down this as standard form of the differential equation. So we get what? We get, and we divide by m. Okay, divide by m, and move those to the left side. Okay, move them to the left side. Let's see. Let's rewrite them. So if we divide by, let's simplify. G minus K over M L. So here I expand them. K over M Y minus C over M dy dt plus 1 over M Ft. So in this step, I just divide by M, right? Divide by M. Okay. And then next, let's see. Mg. Okay, let's see. Let's take a look at those two terms. Actually, this term will be 0 because what? Because if we look at the second graph, in the equilibrium position, this natural length is L0, right? In this equilibrium position, the only force is mg. Is that correct? The only force is mg. So mg in this case, because equilibrium, that means it's stable, it's stay there. So that means mg equals, so we have Fs, we have mg here, so means that they equal to each other. So mg equals them. So if you look at here, you can cancel from here mg minus kl 0. They cancel each other equals 0. Or you can divide by g here, divide by m, g equals kl over m. So this term cancel. Okay. So that means d squared y dt squared, which equals negative k over my minus c over m dy dt plus 1 over m ft. And then write this into like a second derivative and something first derivative. I write down something times y and equals f. We want to write down in this form. This is standard form of the differential equation of order n. So we can write down this as second derivative and plus c over m first derivative and plus just the function y, and the right side is the external force. Right, so we get this differential equation, and our initial conditions are like y0 equals y0, and velocity, that means dy dt 0 is v0, initial velocity. So actually we get an initial value problem, and we can solve this initial value problem. And this initial value problem is also called for if there is no external force, we call that free oscillation. Free oscillation of a mechanical system. And if we just write down ft equals 0. If there's no external force, we say free oscillation, just oscillate by the spring itself, right? So in this class, in this section, we are just going to do the free oscillation. That means ft 0. Firstly, if we want to solve, I'm going to rewrite this initial value problem. I'd like to write down this way. Second derivative plus c over m first derivative k over m, and we make the right side equal 0. We get homogeneous, and initial conditions are like a v0 is just a y prime 0, which is v0. Okay, so first case, there is no damping force. If there's no damping force, that means what? Means c equals 0. That means there's no damping. So our differential equation becomes what? Let's write down our differential equation. Second derivative plus, so there is no first derivative anymore, just k over m y equals 0. Is that right? And for simplicity, if we want to solve this differential equation, for example, if we get something like r squared plus y prime plus, for example, if plus 4y equals 0, what is solution? Do you still remember in 8.1? So this will be r squared plus 4 equals 0. That's PR, right? And r equals cosine 2 theta and sine 2. So here 2t and cosine 2t because the variable is t. Cosine 2t will be the two solutions. Okay, and so for simplicity, we want to make this number to be something square. So we set this to be omega square. Okay, so we let k over m equals omega square. Don't worry too much. We just want to make the equation simple. Okay, then our second derivative, the equation becomes what? Omega square y equals 0. Okay, it's a little bit easier to see. It's better. And here, omega definitely is square root of k over m. So the general solution corresponding to this one, we know how to solve this, right? So it's going to be like r squared plus omega squared equals 0. So as we said, you can think about the example here. R equals plus omega I, because it's plus something, right? Plus. Okay. So what is general solution? General solution should be C1 cosine omega t plus C2 sine omega t. So similar to sine 2t, cosine 2t there. Okay, so this is our general solution in this case when there is no damping force. But next, we want to write down our solution in another form, because from this form it's hard to see what is the real position for this object. So we want to change this into another form. So take a look. Firstly, we draw a right triangle. Actually, we want to combine those two terms together into like a one cosine function. Okay, I'm going to show you how to do that. So we do, this is C1, C2, and we say this is A naught, and this equals, because the right triangle, so C1 squared plus C2 squared, right? And then we say this is the angle phi. So C1 equals what? We want to rewrite this a little bit. So C1 equals A naught times cosine phi, and the C2 equals A naught times sine phi. So our function solution becomes A naught cosine phi cosine omega t plus, we replace C1, C2 by those two, sine phi and sine omega t. And now we can combine them by using the trigonometric identities. So cosine, so we are going to use cosine A cosine B plus sine A sine B, which equals, we want to use this formula, equals cosine A minus B. Okay, so in this case, A naught cosine omega t minus phi. And you can also do phi minus omega t, but they are the same thing. Cosine phi minus omega t equals cosine omega t minus phi, because cosine theta equals cosine negative theta. That's the property of the cosine. So it doesn't matter the order, okay? And we like to write down omega t in front. So this is our solution. We want to rewrite our solution in this case, because in this case we can see what is solution. Solution is going to be a cosine function. The motion, and we can see is periodic motion. Yes, periodic. Because we know cosine function looks like, if we draw the graph of cosine, looks like, okay, so if we have cosine just theta, it looks like this, right? And if we say y equals 2 cosine theta, so we just change 1 here to 2, so kind of like that. So A naught is implicitly, it's like what's the coefficient in front of cosine, and omega give us frequency, and the phi give us like we shift. So for example, if we say do you know how to draw the graph of, for example, y equals You know how to draw this one, right? If I say how to draw this graph, so we just shift the graph to the right side, pi over half. Is that correct? So original graph should be here, and here's pi over half. So we just shift from here to here, something like that. All right. And this is called simple harmonic motion. Here I'm going to give it the definition. If there's no damping force, definition 1. This motion is called, the motion is periodic, and we just say this motion is called simple harmonic motion. Is also called this simple harmonic motion, SH. If I draw the graph of the yt, we know it's going to be cosine function. So here's t and here is yt, and it's cosine, and because a not in front, so actually it's also called the amplitude. Okay, and we shift, so kind of like, let's draw like this way. This is a naught, negative a naught, so it's oscillate between that, right? And here I'm going to give you the name for them. A naught is called amplitude. Okay, what's the length, largest position, and omega is called the circular frequency of the system. And phi is called the phase of the motion, like a shift, how much frequency, phase of the motion. Okay, what's the frequency? What's the meaning of frequency? We can see. We know frequency equals 1 over t, right? And what's t? T is the period. We call the period. For example, if we have function y equals cosine, just cosine t, what is the period? T is 2 pi, right? If we say cosine 2t, we know t equals 2 pi over 2. So y equals cosine omega t, so t equals 2 pi over omega. And what is the frequency? So frequency will be omega over 2 pi. So this depends on the omega. So omega gives us the frequency. And we know what is omega. Omega is root of k over m. So this is the frequency. That means what? Number of oscillations per unit of time. Okay, frequency. So this is the period. This is the frequency. Okay, so this case is pretty easy, right? Because when there's no damping, we can solve this easily. Next case, what are you going to do? Case 2 with damping. That means C is not 0, right? With damping. Okay, so then our second derivative, we should have this term, which is C over M in front, and we still have K over M over this term. Okay, so the only difference is here. We have the first order derivative here. And in this case, same thing, in order to solve differential equation, we do the same thing before. Like if we have just give you regular anything. Probably not 4, give you 5, whatever. How do we solve this differential equation? 5y. We set up PR. Right, so for this case, what's PR? R squared plus C over M R plus K over M. And definitely we want to solve for R. So let's see. Because they are just, general, we have to use the quadratic formula. So here going to be 2a in the bottom, add to the 2a. So which is, okay, 2 negative b plus minus b squared minus 4ac, something like this, right? Okay, and next we want to simplify this a little bit. Let's see, we times m on both, by both top and bottom, times m. So the top becomes negative c plus minus. And when we move m into the square root, it becomes square, m squared, and cancel with the m squared for the first term. And the second term cancel with the m, we still have another m left. And the bottom also times m, which is 2m. This is the solution. Okay, and in this case, when we solve differential equation, we have two cases. Sometimes our R can be real. Sometimes R can be complex. And when they are different, when R is real, we have just e to the ARX solution. When complex, like a plus minus bi, our solution will be cosine bx, sine bx. That would be totally different, right? So we really want to see this term is positive. Okay, so we want to see in under square root, this is positive or negative. If it's positive, we have real solution. If it's negative, we have complex solution. So we want to discuss from here. So we say case 1. Case 1, when c squared minus 4km less than 0. Less than 0, that means what? That means we have complex solution. Is that right? And what is the complex solution? You can see complex solution, I'm going to write down here, negative c over 2m plus minus. So I'm just going to separate them. This gives us the complex part, imaginary part, and this is the real part. This should be the imaginary. So let's see. So our solution will become what? Yt equals e to the real part, like what I said here, right? So negative c over 2m and t times like c1 cosine and plus c2 cosine some t, and that's going to be this complex imaginary part. So here we just, for simplicity, we just write down mu, okay, mu t, and mu equals what? Just this 4km minus c squared over 2m. Okay, in this case, we call that underdamped. Underdamped, I will show you what's the meaning of this. Okay, underdamped means we have complex solution. Oh, just sine cosine, okay? Oscillation sine cosine thing. And the second case is called critical damp. What's the meaning of this one? That means when the thing under the square root equals 0, So what's the meaning of that? That means we have our solution will be R just will be negative C over 2m, and with multiplicity 2 is kind of like for example, if kind of like R minus 2 squared equals 0. For this quadratic function, like R squared minus 2 4R plus 4 equals 0. It's something like this. For this quadratic function, it has two solutions, but those two solutions are the same thing. Okay, same. Repeat twice. Right? So in that case, and what is the solution? The solution will be e to the at, but it repeated twice. That means e to the at, and the other one should be t e to the at, right? And we add C1, C2 in front. And if we simplify, so we like to write down this form. C1 plus C2t. This is called critical temp. Critical temp. Next case is called overdamp. That means when c squared minus 4km is greater than 0, that means we have the real solution for R. Real solution R. In that case, yt just equals to this one. Okay. Same thing, we can solve that. Here should be c over 2m t. That's the real part, and then another real part. Okay, c2 e to the negative mu t. Something like this. And the same thing, mu equals. Okay, I know here looks complicated. Don't worry, I will give you the exact solution. So if we, by looking at the solution, we have all the numbers. We have C, we have M, we have T. So it will be easy to solve. Okay, so here is just general, more general solution.